As practice shows, it is quite simple to make a charger from a computer power supply if it uses a TO494 chip or its equivalent as a PWM chip. But if the unit uses specialized microcircuits, such as 2003 or 2005, then remaking such a power supply is not so simple. I will now remake the board of one of these blocks. This block contains a microcircuit marked 2003. This microcircuit controls not only the operation of the key transistors, but also monitors the voltage on all three buses, 3.3, 5, and 12 volts. In general, remaking the power supply on a 2003 charger chip is not so simple. Before starting the rework, you need to inspect the board and the elements on it for damage that will prevent it from working. My payment on the back has temperature staining, but this is not critical since the tracks themselves are fine. On the board from the elements side, I visually check the condition of the components. I look for chips, darkening, and swelling. Particular attention should be paid to electrical capacitors. Over time, in such blocks, they tend to swell and lose capacity. One of my high voltage capacitors turned out to be swollen. These two capacitors work in pairs, so both capacitors will have to be replaced. I drink the old ones and solder in their place other still working capacitors. Now let's connect the board to a 220 volt network and find out whether it works or not. I connect the 12 volt output to a multimeter with a measurement limit of 20 volts. I connected 220 volts through a light bulb, which in case of failure will simply light up. And here is a jumper with which I will now connect the green wire to the black one. I apply 220 volts and see a light bulb flash. This means the capacitors are charged, and so far everything is going well. Now I connect the green wire to the black wire with a jumper, and a voltage of 12 volts appears on the multimeter. Great! The board is working, but you need to keep it turned on for a while since for some reason the PWM controller may go into protection. And you will need to look for why. After several starts, my board starts up stably, which means that I am starting to further rework this board. To make it more convenient to work further, you need to unsolder all the wires. I'll leave only black, yellow, and green to run the board. This is what the circuit diagram of this power supply looks like. At pins 3, 4, and 6 of the PWM controller, the voltage on the output buses is monitored. If there is a deviation in any direction of at least one of the buses from the reference voltages, then the unit goes into protection. And if the voltage is within the normal range, then the unit continues to operate in normal mode. To fool the PWM controller, I will simulate these voltages. To do this, you will need 2 voltage stabilizers for 12 and 5 volts and a tuning resistance of 100 kilo ohms. Everything needs to be soldered into this one small board. Here is its diagram on the right. Then you need to apply power to the input and check the voltage at the outputs of the stabilizers and set the trimmer resistor to 3.3 volts at the output. Here is a diagram for connecting the decoy. First, pins 3, 4, and 6 of the 2003 microcircuit are cut off from the entire board by simply cutting the tracks. And as in the diagram, we connect a snag with fixed directions. We connect the minus of the blend to the minus of the board and the plus to a jumper on the board. This jumper has 16 volts, and I found it with a multimeter in voltmeter mode. Now we supply 220 volts and check that there is 12 volts at the output. That's the deception itself. Everything works, it doesn't go into defense. And this is how it is located. 3 voltages go directly to the PWM controller. Overall minus, plus on the jumper 16 volts. If everything is fine and the power supply starts up, you can start adjusting the voltage. In order to understand which elements are responsible for voltage regulation and then replace them, let's first compare our board with a circuit diagram. Circuit 14 of the PWM controller pin contains all the elements that are responsible for voltage regulation. First, according to the scheme, there are C24, R45. They are here to ensure that the board works stably, so we will not touch them further. Even further along the circuit, there is an RC chain consisting of capacitor C30 and resistor R57. This chain is also here to increase the stability of the board. Therefore, we do not touch it further either. Next in the circuit are a resistor in which form a voltage divider. In one arm, there is a resistor R38, which I have not soldered, and R39 and R40. The second arm contains R60 and R62. I leave all three resistors that go to negative, but I unsolder the resistors that measure the voltage R60 and R62, and instead of resistor R60, you need to solder in a tuning resistor, which before soldering it here needs to be set to the same resistance of 120 kilo ohms. Here is this resistor R60, and just in case I'll check its resistance. I will use a construction resistor in a package like this. I bend one of the outer legs, it won't be needed. And after twisting it, I achieved a resistance of 120 kilo ohms on it. Then I spread its legs like those of the R60 resistor and installed it instead. And of course, he soldered it. This is what the test bench looks like. And now we will try to regulate the voltage. 220 volts passes through the black wire and goes through the light bulb to the power supply board. If something goes wrong, the light will simply light up. And this is the same decoy that was collected earlier in this video. In order for the power supply to automatically start its green wire, I connected it to the common wire through this wire. I connected this small voltmeter so that I could monitor the voltage online. The black wire was connected to the common wire, and the red and white wires to the 12-volt line. The black and common wires were connected to one of the terminals of the light bulb, and the yellow wire is the 12-volt output. I will connect it to the second terminal of the light bulb. We supply 220 volts and watch the light blink. With this primitive method, I will add contrast to the voltmeter. Now let's connect the light bulb and see how it lights up. Everything works. The light is on. The power supply does not go into any protection. In principle, the rework has already been a success. When connecting a load in the form of a light bulb, a voltage drop occurs, and it is very significant. Having redesigned the power supplies in this way using PWM control, I can say that this drawdown will be less if the power supply is more powerful, but in any case, it will always be there. Now let's also measure the current that flows through this light bulb, a little over 3.5 amps. Well, now the most interesting thing is, what does this tuning resistor give? So using it, you can change the output voltage. You may have guessed the terminals of this resistor, and it will, like mine, reduce the voltage counterclockwise. Now I'm twisting it counterclockwise, and let's see how the voltage decreases. Well, that's it. I reduced the voltage in this case to 9.1 volts. Now let's rotate the trimmer resistor in the opposite direction and see how the voltage rises. I'll try to set it to 14.4 volts, the voltage at which acid batteries are usually charged. When converting power supplies on this PWM controller using this method, I discovered a bad feature. The fact is that when adjusting the output voltage with this constructed register, you should not reduce it below 8 volts, since the controllers on the 13th leg burn out something inside. And then when you try to adjust the output voltage, it jumps between several fixed values. At the minimum, it turned out to be 4.5 volts. Then turning the built resistor sharply jumps to 9.5 volts, and then turning the built resistor, the voltage jumps to 17 volts. But as for the maximum voltage, I managed to get 23 volts at the output with these controllers. At the same time, be sure to look at what kind of electrolyte and capacitors you have at the output. If you plan to keep the voltage at the output of the power supply higher than the capacitors designed for it, then you should definitely replace them. In general, this rework can be considered complete. The charger from this power supply is ready. All that remains is to assemble everything into its original metal case, place it on the case, and bring out 2 plus and minus wires and hang 2 crocodiles on them. It can charge any acid 12 battery. And if you change capacitors at the output with a voltage limit of 25 volts, adjust the output voltage from 16 to 16.5, then it will be possible to charge the calcium acid battery. This is how I converted the power supply. See you in new videos. Bye.